Hey guys, we're going to make a quick video here about electrostatic equilibrium and equipotential surfaces, because those were a couple of things that were, well, that you guys had questions about from the multiple choice the other day in class. So, to begin with, when we're talking about electrostatic equilibrium, what that's referring to is when two surfaces touch and they share charge. So we're talking about charging by conduction, where charge is transferred from one object to another. So over on the left side there, you can see, I pulled a little figure out of our textbook, and they give you these two graphs, right? There's the graph of electric field, all right, so kq over r squared is the curve, and they're doing it for a conductor, so you can see the electric field is 0 everywhere inside of it. When you want to evaluate the electric potential, if you recall, you would take the integral, the area under that curve, and you'd end up with this graph up here, where the potential has, you'll notice, a maximum value right at the surface of the sphere, and then a constant value, everywhere inside of the sphere. That's because it's a conductor, and so the whole thing is an equipotential surface. Alright, so I guess maybe I should bridge from there into what is an equipotential surface anyway, because I keep using that word. To describe that, let's maybe start with a different picture.
So here you can see is an image of the electric field lines around a positive and a negative charge. There aren't really arrows drawn by this app that I was using to make them, so they don't really tell you which one is which, but the plus is the red one and the minus is the blue one. Okay, so the field lines then should point from the plus to the minus. Alright, now there's this equation that we have made reference to several times, which is that potential is the negative integral of electric field. And there's a dot in it for a, I'm trying to make it be a dot, okay, a dot product. The meaning of the dot product there is to say that the potential only actually changes if you are moving parallel to the electric field. That's why it's a dot product. Just like, when we did work equals, the integral of force with respect to displacement. It wasn't just like you could multiply, a force times a distance, actually, because it was an integral that related to a dot product. You had to worry about, whether the force was at some other angle relative to the displacement. So if you had something like this going on where they were perpendicular, and therefore the angle between the force vector and the displacement vector was 90 degrees, you'd get cosine 90, because that's how dot products work. And the result would be that no work would be done by that force. Alright, well, similarly, an electric field only produces a change in potential if you move parallel to it. Meaning there's only really a change in energy as you move through an electric field in such a way that you're moving at least somewhat parallel to the field lines. So that means that if you move perpendicular to the field lines, you're moving across an equipotential surface. So the potential here and here and here, those are all different because the electric field is pointing, roughly speaking, that way. So going that way, following the arrow, gives you a change in potential, right? You're at a higher potential here because you're closer to the positive. Over here, you're probably in negative potential, and directly in between, that's probably your 0-volt line. So if you are looking at 2 points where the potential happens to be the same, like say, there and there, what you're talking about is an equipotential line, or at least 2 points on that equipotential line. If you find many, many of those points, like here, and here. And all of those points, of course, the potential is 0 because of how kq over r works. If you're the same distance away from two opposite charges, the potential cancels out to 0. So everywhere on this line right here, that's 0 volts. Okay. And you'll notice, excusing the artwork and such, that that line that I drew crosses those field lines perpendicularly at every point. So that means that you can draw an equipotential surface by crossing field lines perpendicularly. All right, so if the field lines look like that right there, then, you know, that right there, again, excusing the artwork, might be some kind of an equipotential surface because, as you can see, I'm crossing the field lines perpendicularly. So that means that if I go from that point to that point, the potential should be the same value, should have exactly the same value. There should be no change in potential. So a particle moving along that line wouldn't change in terms of its potential or therefore kinetic energy. It would move at a constant speed. All right. I could draw many more such lines as long as, you know, I'm drawing a line that, you know, crosses perpendicularly to the field lines indicated in this diagram. I'm defining an equipotential surface. All right, so my vague, poorly drawn sketches there, I'll replace now with a much nicer picture. And in this much nicer picture, you can see a whole bunch of equipotential surfaces drawn. And notice they always cross perpendicularly to the electric field lines. And in that way, they show you all the points where the potential is some particular value. I don't know how exactly they graded these things out, but this would be your, the middle one there would be your 0 volt line, okay? And then closer to the negative charge, maybe this is negative 10 volts, negative 20, etc. All right, now you can do the reverse, okay? If you have a sketch of just the equipotential surfaces, you can draw your field lines by drawing lines that come off perpendicular to that. Okay, so if you've got your surfaces there, just imagine that I can't see my field lines. You know, I could draw a line like this that, you know, crosses perpendicularly everywhere, and I've successfully drawn an electric field line based on the equipotential surfaces. Now, the other thing you can get from this, though, is based on one of our other equations, E equals negative dV dx, meaning the electric field is the negative derivative of potential. You can actually use a chart or graph, such as in multiple choice question 13 in your packet, where they show equipotential surfaces to estimate a value for the electric field. Because instead of dV dx, we could say it's, you know, delta V over delta x, and that gets at the same idea, because maybe we don't have a function we could really take a derivative of. Okay, so looking at this picture here, you can see that out here somewhere, the field is actually rather weak, because, you know, if each of these lines is 10 volts, then, you know, this one here is maybe the negative 20, this is the negative 30 volt line. And so you've got a change of 10 volts over that distance right there. So if we measured out and we said that that was like 2 centimeters, then we could say that it was a change of 10 volts per 2 centimeters, so 0.02 meters. And that would give us an electric field of, mental math, 1,500 volts per meter would be the electric field at that point approximately, right? Out here, though, it's also a difference of 10 volts, right, going from this line to that line. And that to me looks like, I don't know, a good 6 centimeters. So if it's 10 volts per 6 centimeters, that's an even weaker electric field. All right, go to a region like over here, and you can see, you know, each gradation there is 10 volts per, I don't know what that distance is, but, you know, easily we're talking about 1/10 of a millimeter. And so in the regions in between these two charges, you've got a big electric field. Okay, so one way to evaluate the value of an electric field is by looking at the equipotential lines. Where they are tightly spaced, delta V over delta X is big. Where they are loosely spaced, you know, such as out here or something like that, then your electric field is much weaker because the rate of change in potential is much smaller. So circling back around now to the subject of electrostatic equilibrium, when you take two conductors, or consider just this fact that we started with, right, that a conductor is an equipotential surface. The whole thing is at one particular potential, right? The whole surface, everywhere inside of it, outside, inside, it's all at the same potential because it's a conductor, and the whole object is an equipotential surface. Well, now, if you do that with two spheres and you touch them together, then they are now one equipotential surface, meaning they have to go to the same potential. Now, the potential at the surface of a sphere is kq over the radius of that sphere. If you take two of them and touch them together, it's a little bit more ambiguous, like, what is the radius of the sphere here? What am I supposed to do with that? Well, it's not like you can just sort of pretend that it's like one new sphere or something like that, or average out the radii or something. The way that it actually ends up working is this. We know they're going to transfer charge until they reach the same, not charge, but same voltage. Okay? So if the total charge starts off as, say, Q, at the end, one of them is going to have a charge of Q1, and the other is going to have a charge of Q2, whatever each of those are. All right, they're also going to go until their potentials are identical, not their charges again, right? The only way that they would exactly evenly share charge is if they were exactly the same size, because as you can see, the radius matters. Okay, the potential on each of them, the potential on each of them at the end is going to be K Q1 over R1, whatever that is, and that's going to be equal to the potential on the other one. All right, and where you would go from here algebraically, I'm not going to work it out. If you want to, you can check out this example in your textbook and see how they do it. But from here, you know, the algebra would be relatively straightforward. You would say, you know, Q1 and Q2 are a ratio based on the radii. Okay, so we could take that and say that like Q1 times, or Q1 equals Q2 times R1 over R2. And if we have numbers or whatever, we could take that and sub it in here. And now we only have Q2 that we don't know. Work out what Q2 is as a fraction of the original charge. And now you're able to determine the charge on each of the two spheres, and if you like, the potential that they each go to. All right, so anytime it's a question with spheres coming in contact like that are conductors, you say, well, it's now one equipotential surface. They go to the same number of volts, and that's when charge stops being transferred. All right, I hope that was helpful. I'll see you in class tomorrow.